Okay, so we're going to start taking a look at the 2017 paper 2. So a number of assumptions are made when explaining a behavior of gas using the molecular kinetic theory model. State one assumption about the size of the molecules. So we assume the volume of the gas molecules is negligible compared to the volume of the container. That's how we can assume the collision time is negligible. And so what we're effectively doing is modeling the gas particles as point masses or objects with no volume. So we've got a diagram showing how pressure changes the volume for a fixed mass of ideal gas, which means we've got a fixed number of moles of gas. The temperature of the gas is 27 degrees at A, and we've got two changes from A to B, which is constant pressure, and then from B to C. Okay, so now we want to calculate the number of gas molecules trapped when it's at situation A. So I'm going to use this equation because the capital N is the number of molecules. So we rearrange it, put in the values of P and V at A, and then make sure we put the temperature in Kelvin, giving us the right number of molecules. Calculate in Kelvin the change in temperature during compression between A and B. We can see it's compression because its volume is decreasing. So first thing, we can notice it's a constant pressure process, which means we can apply this law here to calculate the final temperature as 214 Kelvin. It started at 300, which is 27 degrees, so that's a temperature change of 86 Kelvin, and it's a decrease, so it's minus 86. Okay, so deduce whether the temperature of the gas changes during the compression from B to C. So I'm essentially going to use Boyle's law here. So what I did is I've calculated the product of pressure and volume at each of those two positions, and we can see that it comes out as different values. So if it were constant temperature, those two values should have been the same. So we can see that it's not a constant temperature process. So compare the work done on the gas during the change from A to B with that from B to C. So what we're effectively doing is we're comparing the area under the graph. So if you go from A to B, that's really easy because it's a rectangle, 20 joules. Going from B to C is we've got the same area, but then we need to add on the area above it, which I've modeled as a triangle, because you can see I've done half base times height, giving us a work done of 30 joules, and we can see that essentially the work done from B to C is about 10 joules bigger than the work done from A to B. Okay, so moving on to do some magnets stuff. So we've got two magnets supported on a yoke. So this is one of the experiments you should have done as part of the course. And the magnets produce a uniform horizontal magnetic field in the diagram shown. And we've got a copper wire which is connected in a circuit. We've got a plan view. So we're looking down on the equipment, that means, and the balance is zeroed when the switch is open, when there's no current. This reading changes to a positive value when the switch is closed. Which of the following correctly describes the direction of the force acting on the wire due to the magnetic field when the switch is closed? So if the balance records a positive force, that means the yoke experienced a force downwards from the wire, which means the wire experienced a force upwards from the yoke. So essentially just using Newton's third law. So if the wire experiences a force upwards from the yoke experiences a force downwards, which is why we get a positive reading on the scale. So label the poles of the magnets by putting a north or south on each of the two dashed lines. So essentially, we know the force is going to be up, and if you look back at the circuit diagram earlier, conventional current is going from E to D. So I'm going to got my middle finger pointing upwards in the diagram. We've got my thumb coming out of the page, which means that essentially the field must be going from right to left. So the north is the one on the right and the south is the one on the left there. Define the Tesla. So this is the magnetic field strength that produces a force of 1 Newton on a conductor with a length 1 meter inside a magnetic field, carrying a current of 1 amp at 90 degrees to the field. That's what a Tesla is. So the magnets are 5 centimeters long, the current is 3.43, and the balance reads 0.620. Assume the field is uniform and 0 beyond the length of the magnet, calculate the flux density. So we're going to use F equals Bill. The force is going to be the mass reading times by 9.81, and then just rearranged to make the flux density the subject, plug the sums in, and we get 0.0355 Tesla. Okay, so sticking with magnetic fields, we've got a cyclotron using two D-shaped regions, like you can see in the diagram, and we've got an alternating electric field between the D-shaped regions as well. That is accelerating the charged particle. The magnetic field is there to make them travel in a circular path. So we've got the diagram showing the path of a proton that's being accelerated, going in bigger and bigger circles, and then it's eventually released from the cyclotron. Explain why it's not possible for the magnetic field to alter the speed of a proton while it is in one of the D-shaped regions. So the key to this is the fact that the force is always perpendicular to the velocity. Therefore, no work is done on the proton, so its kinetic energy and therefore speed must stay the same. So the force of the magnetic field acts just to change the direction of the velocity, but not the magnitude. So derive an expression to show the time taken by a proton to travel around one semicircular path is independent of the radius. So if we use our condition of circular motion, BQV equals m omega squared r, instead of tangential velocity, we can substitute in omega r. So then you can see the r's cancel, and omega cancels with the power of 2, leaving us with this expression. We can then put 2 pi over t in place of omega, make t the subject, and you can see that the time period only depends on the mass, the flux density, and the charge. There is no radius in there. Okay, so the maximum radius of the path followed by the proton is 0.55 meters. The flux density is 0.44 Tesla. Ignoring any relativistic effects, calculate the maximum speed of the proton when it leaves the cyclotron. So I'm going to essentially figure out what velocity we can have at the biggest radius. So we've got BQV equal to mv squared over r. Cancel the v's and make v the subject, means we've got BQR over m. Plug the numbers in and we get the velocity is 2.3 times 10 to the 7 meters per second. Okay, so moving on to something different, we're now looking at a nuclear reactor. And we've got a number of components exposed to moving neutrons. So first of all, state what happens to a neutron that is incident on the moderator. So the moderator is there to slow our neutrons down. So the neutron collides with the moderator particle, usually water, or the hydrogen specifically inside water, and it transfers some of its kinetic energy, causing the kinetic energy of the neutron to decrease. State what happens when a neutron is incident on a control rod. The control rods are there to absorb neutrons to make sure we stay at critical mass in our reactor. So a slow-moving neutron is in a collision with a nucleus of an atom of the fuel, which causes fission. Describe what happens in the process. Okay, so first of all, the uranium-235 is what's in our fuel rods, so it absorbs the neutron through the strong interaction. So we've gone from neutron 235 now to uranium 236. Now, uranium 236 is unstable, so this is when fission occurs. So we call the 236 the parent nucleus. It undergoes fission to produce two daughter particles, and they can be a range of different types of particles, but it also emits several very high kinetic energy neutrons, which is how it can then produce a chain reaction. Okay. So a nuclear reactor produces radioactive waste. State the source of this waste and discuss some of the problems faced in dealing with the waste at various stages of its treatment. Your answers should include the main source of the most dangerous waste, how the waste is treated, and the problems faced in dealing with the waste, with suggestions for overcoming these problems. So, first of all, the first problem we have to deal with is the fact it's very hot. So the dangerous waste is in the fuel rods because it's the daughter particles of the nuclear reaction. So to deal with that, we need to cool them down. So we put them in something called a cooling pond, and we do it for a year, or if not several years. Okay, so that's our first problem dealt with. We got rid of the fact it's really hot. The next problem is we have a range of different particles, so we're producing alpha, beta, and gamma radiation. So to deal with that, the first thing is we try and take any useful nuclear fallout of it. And the next thing we do is we turn it into a solid so it can't leak out. So we turn it into a solid glass type material, and that process is called vitrification. So we don't really want liquid, we want it solid. It's much easier to store. And then because it's an alpha, beta, or gamma emitter, we are going to put it in stainless steel barrels, and we're going to seal them so no alpha radiation can leak out and beta radiation is absorbed by the steel. And we still haven't addressed the gamma radiation, so what we do is we bury it deep underground, and that absorbs any gamma radiation that could be emitted. And we don't really want to be transporting these around because they're emitting gamma radiation, so this is done very close to the nuclear power plant. Okay, so we're sticking with nuclear physics, but now looking at binding energy. So we want to calculate the binding energy in mega electron volts of a cobalt-59 nucleus. And we're told what the mass of a cobalt-59 nucleus is. So to get the binding energy, we need to first calculate the mass defect. So going to my data booklet, we can get what the mass of a proton and a neutron actually are. So we can calculate what the mass of a cobalt nucleus should be, and then we can find the mass defect. So what I've done there is I've taken the mass of it. The mass was in times 10 to minus 26, so I've turned that into 98, so they're both times 10 to minus 27, and calculated the mass defect. And then what I've done is I've used E equals mc squared to convert the mass defect into joules, and then divided by 1.6 times 10 to the minus 13 to calculate it in its binding energy in mega electron volts. So this is one way of doing it. There are several ways of doing this calculation which produce slightly different values of binding energy depending on how you do it, but this would be the way I would do it using the data we've got. So a nucleus of iron-59 decays into a stable nucleus of cobalt-59, and it decays by beta minus emission, followed by the emission of a gamma radiation to get it into ground state. The total energy released when it decays is 2.52 times 10 to the minus 13 joules. The iron-59 nucleus can decay to one of three excited states of cobalt-59 shown, and we've got the different energies. So they're all produced by emitting a beta particle, but the beta particle has a range of different kinetic energies to then mean we end up in different energy states of cobalt. Okay, so calculate the maximum possible kinetic energy in MeV of the beta minus particle emitted when the iron-59 nucleus decays into an excited state that has energy above ground state. So to have the maximum energy of beta minus particle, we're going to go into the n equals 2 level, so the excited state just above ground state. And we're going to assume the neutrino doesn't have any kinetic energy. That's how we get maximum for the beta particle. So I'm going to find the difference between the total energy of the iron and the minimum excited state of cobalt, and the difference between those gives us the energy in joules, divided by 1.6 times 10 to the minus 13 gives us the kinetic energy in MeV. So following the production of excited states of cobalt-59, gamma radiation of discrete wavelengths is emitted. State the maximum number of discrete wavelengths that could be emitted. So let's go to our diagram. So I've drawn the possible changes that could occur which indicate different photon energies. So starting at the highest energy level, we could go straight down to ground state. We could go to n equals 2, then to ground state. We could go to n equals 3, n equals 2, or we could go from n equals 2 to n equals 3 to n equals 1. So you can see there are 6 different energies that we could essentially produce. So there are 6 wavelengths of photon. So in terms of the longest wavelength, we want the shortest energy transition, or the smallest energy gap, which is between 2.29 and 2.06 times 10 to the minus 3. And once we've got the energy, we can then calculate the wavelength using this equation, like I've done here. Okay, so moving on to gravitational fields. State what is represented by gravitational field lines. Well, they tell you the direction a force would be experienced by a mass in the field. So we've got the gravitational field above a small region on Earth. Suggest why the field lines converge over a small area at K. So if the field lines are closer together, that means the field is slightly stronger at that point. So the reason I've come up for that, so it would be that we've got a slightly higher density at that particular point on the Earth. Maybe the materials that are making up at that point are slightly more dense. So a ball traveling at constant speed passes position J moving towards K. So assuming friction is negligible, explain any change in the speed of the ball as it approaches K. So the thing to realize is if the gravitational field gets stronger, that's going to mean the gravitational potential decreases slightly. And that means if the potential energy is decreased, that means the kinetic energy is going to increase. So the speed is going to increase. Okay, so we've got a diagram showing the lines of force for an electric field surrounding two charged objects, L and M. Explain why the field lines of force shown in figure 7 cannot be a gravitational field. Well, you can see that they're traveling away from object L. That is not possible with a gravitational field. Field lines always have to travel towards objects. Which object has a charge with the greatest magnitude? It's L, because you can see the field lines are much closer together. Which has a positive charge? Again, it's L, because the field lines are going away from L towards M, so they're going from positive to negative. Okay, so draw on figure 7 an equipotential line that passes through point N. Do not extend your line beyond the given field lines. Okay, so in terms of drawing this line, what I'm trying to do is draw a line that joins, essentially we have equal sized gaps between the field lines. So I want to find a point where the gaps between the field lines are approximately the same length, which is why they bend round at the top. We're trying to follow the points where the gaps between the lines are the same, indicating that the field strength is constant, which means the potential is constant, essentially. Okay, so derive an expression to show that for satellites in circular orbit, t squared is direct proportional to r cubed. So we're just equating our Newton's law of gravitation with our expression for circular motion. Cancel the m's, substitute in 2 pi over t for omega, rearrange to make t squared the subject, and we can see that r cubed is multiplied by a constant, so we've shown that t squared is directly proportional to the radius cubed. So Pluto is a dwarf planet. The mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers. The mean orbit radius of Earth is 1.5 times 10 to the 8 kilometers. Calculate in years the orbit period of Pluto. So what we can do is make t1 squared over r1 cubed equal to t2 squared over r2 cubed. Make t2 the subject of that equation. The distances are both in kilometers, so we can just put those as a fraction. The time period for Earth is 1 year. So in terms of Earth years, Pluto has a year orbit time period of 247 years. So a small mass released from rest just above the surface of Pluto has an acceleration of 0.617 meters per second squared. Assume Pluto has no atmosphere to provide any resistance to motion. Calculate the mass of Pluto, giving your answer to appropriate number of significant figures, and we've got the radius. So if there's no resistance, that means the force is due to the weight force of the object, which is due to the gravitational field. So we essentially know what the gravitational field strength is, so we can rearrange that to make mass the subject, plug the values in, giving us the mass of Pluto, and all of those numbers are 3 significant figures, so our answer should be 3 sig figs 2. So we've got a graph showing the variation in gravitational potential with distance from the center of Pluto, and we've got that for points below and above its surface. We've got a meteorite hits Pluto and ejects a lump of ice from the surface that travels vertically at an initial speed of 1400 meters per second. Determine whether this lump of ice can escape from Pluto. So we first need to work out what the gravitational potential is at the surface of Pluto where the collision happened. And that's about minus 7.4 times 10 to the 5 joules per kilogram. So if it's going to go from that potential to 0, we need to make the kinetic energy equal to the change in potential energy, or essentially half v squared equal to the change in potential, because the mass cancel. And then we can rearrange to make that the velocity of the subject, plug the numbers in, and we can see that 1400 is bigger than that, so it can escape. And that completes this paper.